Let us start by motivating ourselves about canonical transformations. Now, let us consider a system with n degrees of freedom and described by a Hamiltonian. So, the Hamiltonian of the system, which is function of q, p and t. Okay. So, typically of course, you write down the equations of motions, which are q dot is equal to partial derivative of h with respect to p and p I dot, which is minus partial derivative of q I, and here of course, I goes from 1 to n, and the job is to integrate this system. Now, when does this become really trivial? A trivial case is when all the coordinates are cyclic. Okay. So, if all coordinates are cyclic, then we know what happens. If all of them are cyclic, then p I dot is 0 for all I. Okay. Now, that means p i's must be some constants. I will put these constants by alpha I. And look at now what happens to Hamiltonian. Because all the coordinates are cyclic, they are absent from Hamiltonian. So, your Hamiltonian is just function of all the generalized momenta or canonical momenta, and those remain constant. So, it is function of this, and this immediately has a consequence, because then q I dot is nothing but partial derivative of h with respect to p I, but this itself will be function of p i's, and p i's are constants. So, this in fact would be function of alpha 1 to alpha n. We will write this as a constant as omega I, and this solves the system completely, which is q I as a function of t, then is omega I into t plus some q I 0. Okay. So, we have solved the problem entirely. Now, can I do this for every possible system or every system? Are there transformations which help me find? So, what we do here is make a transformation, so that I go to a new system or new variables. In the new variables, I have all coordinates which are cyclic. Take for example, if I take a case of central potential, what would be your Hamiltonian? Hamiltonian, if written in the variables x, y, p x, p y, then in this one the Hamiltonian is p x square by 2 m plus p y square by 2 m and plus the potential energy, which is function of square root of x square plus y square. Now, in this case, you can see that x and y both will appear in the Hamiltonian. None of these two coordinates are cyclic. Now, make a change of variable. We already know that the plane polar coordinate would be a more suitable choice here. So, if I make a transformation from p x p y to r theta p r p theta, what would Hamiltonian look like? Hamiltonian looks like p r square by 2 m plus p theta square by 2 m r square plus u of r. And now you notice theta is cyclic. If theta is cyclic, number of constants of motion that we can find out here is 1, and we can immediately write down p theta square by 2 mr square. This must be equal to some Lz square, okay, some constant there. So, the number of cyclic coordinates is actually dependent on which coordinate frame or which canonical variables you are using. Now, this opens up a question: can I find a transformation from the old coordinates to new coordinates, say from all the coordinates to new coordinates, such that all the new variables are cyclic variables? If we can do that, then the problem becomes trivial and it can be solved in this way. It can be completely solved in terms of the initial conditions there. Okay. Now, the notion of these transformations, remember these are the transformations in phase space. The notion of transformations we have been already using in the Lagrangian formulation. Remember, we in fact made that as a big advantage of the Lagrangian formulation, that in the Lagrangian formulation you can keep on changing the set of generalized coordinates, and what happens when you do that? So, in the Lagrangian case, Lagrangian formulation, you start it's built on the top of the configuration space. So, you take variables q. So, you have a Lagrangian which is function of q dot t. So, you have a system which is described by this Lagrangian, and now what we want to do is make a transformation to some new variables s, and s of course are expressed in terms of q and t. So, it is a transformation from q to s, and the transformation itself is probably time dependent. Now, in this case we know how to construct the new Lagrangian. The new Lagrangian L tilde is written in terms of the coordinates s, s dot and t, and remember L tilde is actually same as L. That means, the value of the Lagrangian at a point in the configuration space and for given velocity is exactly same. All that is happening is the coordinates of that point are changing. So, L tilde here, which is function of s, s dot and t, this also must be equal to, and this is of course the definition of the transformation. So, all the functions would transform like this, would be you have to write Lagrangian, but now take all the old variables and transform them to new variables. So, write q as a function of s and t. Remember, for that you have to invert this equation, and then q dot is written as function of s, s dot and t, and maybe time itself. Okay. So, this is a simple procedure. You have a function, you take the old coordinates and somehow find the new coordinates through the transformation equations and substitute, and you get the new Lagrangian there. And the great thing that happens here is the form of the equation, form of Lagrange's equation is invariant. Equations is invariant, and what that means is if the original Lagrange's equation partial q dot minus q, if this is equal to 0, then this necessarily implies that d by dt of partial of L tilde with respect to s dot, I should of course put the index there too. So, S I minus S I is equal to 0. This is of course the great thing that happens with Lagrangian mechanics, and also considered as big change from Newtonian mechanics to Lagrangian mechanics. See what happens in Newtonian mechanics. I take in a plane, for example, I start with the Cartesian coordinates. The equations are straightforward. Mx double dot is equal to x component of the force, my double dot is equal to Fy. Okay. But if I make a change of variables to r and theta, now the equations do not very simply look like mr double dot is equal to r component of force. Okay. They do not. So, the form of Newtonian equation changes with changing coordinate system. The great thing that happens with the Lagrangian formulation is that the form of Lagrange's equations or Lagrange's equations are form invariant under the coordinate transformations, okay, or any generalized coordinate transformation. And these transformations have a special name, they are called as point transformations. And this happens because of one reason. See, when you change from old coordinates here q to new coordinate s, what happens is this: the s dot variable is not free to change. You see, it is not a transformation of q to s and q dot to some other s dot. S dot changes in a very specific way. So, s dot will be given by sum over I. So, if I write this as S I, then I will take sum over j, then this will be del S by del q j dot plus the partial derivative of S I with respect to time. So, you see this transformation actually transforms only n variables which are generalized coordinates. The velocities are forced to change according to this rule. This is what makes the form invariance possible. Okay. Now, when you go to phase space, this transformations in phase space, when you go to phase space, the transformations in phase space, remember there are 2 n variables there, which means I have q and p, all these now can change to capital Q and capital P. Now, this poses a little bit of complication, okay? And this also will probably give you wider set, because remember your p variable, the conjugate momenta or canonical momenta are connected to the generalized velocities there in the Lagrangian formulation, and those velocities were not allowed to change arbitrarily, but here the momenta can change arbitrarily. You can, if you can think of any transformation here, that of course would be independently q changing and p changing. So, if I write this as new variables q I is equal to q I, which is function of old variables, and p I, sorry, yeah, p I old variables. Okay. Now, what is the complication here? You see, when I got the Hamiltonian from Lagrangian, when we get that, then if I make a coordinate transformation in the configuration space, then of course my q and q dot changes to s and s dot. That also gives you p for q variables, if I call them as p q, and then there are p s. But you see, the Hamiltonian is a legend transform of the Lagrangian, and there what we are doing is we are replacing q dot variable by the p variable. But now in 2 different cases, they are likely to be different. Will the Hamiltonian H for a given system, if I make this transformation, what will happen to this Hamiltonian? Will this Hamiltonian remain unchanged? No, it changes too. Probably the Hamiltonian is completely different from the original Hamiltonian. What I will do is I will take one example to specify or to illustrate this point. Let me start by just constructing the Lagrangian for a free particle. Let us just keep this simple. I will assume that the particle moves only on one line, So, there is only one degree of freedom in the problem. The Lagrangian is mx dot square. What is the corresponding momentum? That is Px, and that would be equal to mx dot. And we also know how to construct Hamiltonian from here. The Hamiltonian, remember, is function of x, Px and t, and this would be Px square by 2m. And what are the equations of motions? So, equations of motions here would be Px dot would be 0 because x does not appear in this Hamiltonian, and x dot will be equal to Px by m. So, these are your equations of motion, remember. Now, we want to make a transformation. When we make a transformation, I will write y, the new variable, as x plus some v naught times t, where v naught is this, v naught is a constant, and I will define Py same as Px, leaving Px unchanged to Py. Okay. Now, if I do this, then so this is a coordinate transformation from x Px to y Py. How do I calculate my Hamiltonian? I can calculate my Hamiltonian. I will call this as H prime, which is Hamiltonian of y, Py and t. And if you write this as H, so this is something that we did for Lagrangian. When I went from one coordinate system to another coordinate system, how did the Lagrangian change? The new Lagrangian L tilde is obtained from the old Lagrangian by simply substituting for the old variables the new variables. Okay. So, let us do that here too. So, that means I should write this as x in terms of y and Py and Px in terms of y and Py, and possibly if t is, in our case of course t does not appear in the Hamiltonian. And what would be this Hamiltonian then? This one will be equal to Py square by 2m. Remember, there is only Px square by 2m in the original Hamiltonian, and Px is equal to Py in the transformation which we are considering here. Okay. Now, let us construct the equations of motion. If I were constructing equations of motion, then y dot, so y dot will be equal to x dot plus v naught. Okay. And what is x dot? So, what I am doing is I am taking these equations of motion and constructing them here. So, we start with this equations of motion and try to construct equations of motions here. So, if I take y dot, that is x dot plus v naught, but what is x dot? X dot is nothing but Px by m plus v naught, and what is Px? According to our transformation, it is Py by m plus v naught. And the second equation will be, so this is the first equation, and the second equation will be Py dot, but then that is same as Px dot and will be equal to 0. Okay. If I make this transformation, I get new equations of motion. Look at, can I derive them from this Hamiltonian now is the question. So, I am going to do this in two different ways. I have a transformation, I take this transformation, use the transformation to transform equations of motion. Now, what I am going to do is first I am going to transform Hamiltonian to new Hamiltonian and construct the equations of motion. Okay. Let us do that. So, here if I look at del h prime by del Py, then what I get is Py by m. Okay. And this is in fact according to it's y dot. So, that would be sorry. So, that would be m y dot. So, y dot plus v naught. Now, there is a problem here, because the equations this we were expecting according to the equations of motions or Hamilton's equations, this should have been equal to y naught, and that is not equal. So, which means y dot. So, y dot in this case is not equal to del h prime by del p y. So, here you see I need to somehow recalculate the Hamiltonian, the new Hamiltonian. The old Hamiltonian and this Hamiltonian, the way I have constructed it, is not correct. This will not give me the correct equations of motion. So, how do I construct the correct equations of motion? One of the ways to do that is go back to your Lagrangian and recalculate. So, once you have these transformations here, you go back to Lagrangian, and from Lagrangian you calculate P y, that still will be equal to P x, but now calculate the Legendre transform of L tilde, and when you calculate Legendre transform of L tilde, you get H tilde, and this H tilde will be equal to, I will leave it as an exercise for you people, show that this in fact will be equal to P y square by 2 m plus V naught times P y. Okay. So, what did we do? We had H prime, which we simply like you take any function on a domain, you change the coordinate system, the function is redefined this way, but not in this case. The new Hamiltonian must be found from the Lagrangian. Now, we of course do not want to refer to the Lagrangian in first place. I want to do the entire process here of transforming variables from the old coordinates, new coordinates in phase space here itself without referring to Lagrangian. So, that means I am looking for specific kinds of transformations, the specific kind of transformations which leave Hamilton's equations unchanged. So, let me define the canonical transformation. Okay. So, in the phase space you make a transformation from q p to capital Q p, okay, capital Q and capital P. Let me write these transformations as again q I, which are given as functions of q, p and t, and p I, which are functions of q, p and t. I will call this transformation. So, this transformation is called canonical transformation. If we can find some new Hamiltonian, so if there exists capital K, which is function of capital Q, capital P and T, function of new variables, such that Q I dot is del K by del P I, and remember this is capital P I dot is equal to minus del K with respect to new variable del Q I. Now, question is this. So, the transformation is called canonical if it preserves the structure of the Hamilton's equations. Now, we already are familiar with such an idea. See, in general, in the phase space you can make any arbitrary transformation, but those transformations will not preserve the structure of the Hamilton's equations. We are looking for special transformations which do so. Now, where else we have seen this? In case of Newtonian mechanics, you see, you take your Cartesian coordinates x, y, you go to new coordinates r theta, the structure of the equation changes. But wait, there are specific transformations which are called orthogonal transformation. That means, you merely rotate the coordinate frame and what you get is a new Cartesian frame. That means, new x prime and new y prime, they are still perpendicular to each other. What happens to the Newton's equations or structure of Newton's equations there? It remains invariant. That is, m x prime double dot is equal to f x prime, the component of force in the x prime direction, and similarly for y prime. So, among all the possible transformations that you can have, coordinate transformations that you can have in the plane, there are some special transformations which preserve the form of. Okay. Now, same thing when you go to Lagrangian, you make any coordinate transformation, it always leaves the form invariant. You come to phase space, any arbitrary transformation will not preserve or may not preserve the form of the Hamilton's equations. We are interested in the ones which preserve the form of Hamilton's equations. Okay. So, this is what we are trying to find. New transformation also must, after transformation, new canonical variables also should satisfy Hamilton's equations. Now, question of course would be, for a given transformation, how can I find or how can I decide whether it is a canonical transformation or not? And second question that we would like to ask is, given a Hamiltonian, how can I find k, okay, the new Hamiltonian? Remember, when I am talking about canonical transformations, they do not depend on a specific system, they do not depend on a particular h and finding particular k. I must speak in terms of generality. This transformation or this definition of canonical transformation is independent of any specific system that we are talking about. This must happen in general. Okay? This must be, if it is canonical transformation for free particle, it is a canonical transformation for all possible systems defined on this phase space. Okay. Now, in the next few minutes, we will try and find a condition which will tell us whether a given transformation is canonical or not, and also how to go from h to k, or how to find the new Hamiltonian k. Now, before we try and find the condition for canonical transformations, let me first bring back the Hamilton's principle. Remember, the Hamilton's principle for Lagrangian formulation was that in the configuration space, you try to find a path or a trajectory between 2 points at given 2 times. The path is the one which minimizes this action. Okay, that is your Hamilton's principle. Now, do I have a similar Hamilton's principle in Hamilton's equation or Hamilton's formulation? So, think of it like this. I have the phase space, okay. There are these q variables and there are these p variables. It is a schematic diagram, and then you take one point here and the other point here, and then we are looking for a path of the system, and of course, we know that this path satisfies the Hamilton's equations, but how to get Hamilton's equations from some sort of a Hamilton's principle, some sort of a least action principle, and that is what we will look at first. Now, I will just remind ourselves that if you have some sort of a action which was integral from t1 to t2, and then some function of these variables. Okay. So, variables I will just here write it as x variables. So, x1 to xn, and you have x1 dot to xn dot and independent variable t dt. Okay. We already know that this action is stationary if there is a Euler-Lagrange equation. So, that would be d by dt of partial of f with respect to x I dot minus x I, and this must be true for all I. Okay. Now, I want to apply this for the Hamiltonian formulation. So, let me define here the integrand as t1 to t2, and here I will write it as p q dot, and remember there is a summation implied, or I will write this as p I q I dot minus the Hamiltonian, which is function of q, p and t dt. Okay. But the trick that you have to do is this: think of this as an integrand function where the independent variables are qi's, q1 to qn, pi's, p1 to pn, and q dots and also p dots. So, qi dot, pi dot, and possibly this time t. Okay. So, you see what we have done. Now, the integrand, in the integrand, earlier our pi and qi dots were related, but not here. Here I am going to treat them as completely independent variables. Now, let us apply the Euler-Lagrange equation to this. So, this will be minimized or has a stationary point, if, so it would be d by dt of del f over del q I dot minus del f over del q I is equal to 0. And what does this give us? This gives us, so this function depends on q dots through this, remember here. So, through this, but q dots do not appear in this one, in the Hamiltonian. So, it would be d by dt of p I minus, and q I variable does not appear in the first term here, it appears only in the Hamiltonian. So, this would be minus del h over del q I, this must be equal to 0. This gives you our first equation, p I dot is equal to del h over or partial of h with respect to q I. The second equation, remember p i's are also independent variables. So, d by dt of del f over del p I dot minus del f over del p I, this also must be equal to 0. And what does this give us? P I dot just does not appear in the equation at all. So, there is no p I dot in this, which means del f over del p I must be equal to 0. So, that would be, so when you take a derivative of this with respect to p, I get q I dot minus, so there is a q I dot minus minus q I dot minus del h by del p I is equal to 0. This gives you the second equation, q I is equal to del p I. Sorry, this would be plus, this would be minus, and then you have plus minus, yeah, now it is correct, right. So, this is how we get the Hamilton's equation by some sort of a action principle and some sort of a modified Hamilton's principle there. Now, this one here, if I for example add a total derivative of some function into this, remember this result we had seen when we were doing a variational principle, that if I for example take that integrand, and so there is a summation over p I q I dot minus h, and if I add a total derivative of some function of p and q and t to construct action like this. What happens in this case? Oh, you get exactly same equations of motion. Why? Because remember this term here being a total derivative, where does it contribute? It contributes only at the end points, but at end points the variation in this function is 0, which means this term actually does not change your equations of motion. Now, let us come to the condition for canonical transformations. For the condition, now what we are going to say is this: I have original variables, you make a transformation to new set of variables capital Q and capital P, and then the equations or the Hamiltonian in the old set is given by H, and we want to find this new Hamiltonian, or new Hamiltonian is given. Both these will have the same equations of motions, or the structure will be preserved if they are drawn from the same Hamilton's principle. That means, what we are looking for is this: the variation of integral from T1 to T2 of P I Q I dot minus H dt, and this must be equal to same variations in the new variables. So, it will be sum over I capital P I Q I dot minus capital K dt. So, if this happens, then you get same equations of motion. Now, because these variations or these two functions have same stationary point, does not mean that they are necessarily equal. What must happen? They can differ from each other. Q I dot minus H minus sum over I P I Q I dot minus K. This difference must be equal to some total derivative of some function. Okay. Now, in the earlier case, we could have, of course, you could have added this term to the left side, in which case you would express this capital F as a function of small q I and small p I. If I add this to this side, then this capital F is looked upon as the function of capital Q and capital P. But you see, you really have this transformation here, transformation which connects the old set of variables to new set of variables, that is q I is equal to q I, which was function of q, p and t. And here P I are given as Q, P and T. Now, in fact, I should be able to write this function f as a function of not just small q and small p or capital Q and capital P, but can I possibly write those as functions of small q's and capital Q's? Sure, I can do that because I have these transformations here. So, if I, for example, I can invert these transformations to write the function f in terms of small q and capital Q. So, what this says in that case? In that case, it says is if I take dt to the other side, then sum over I P I dqi minus sum over I capital P I dqi dqi plus k minus h dt. This must be equal to d.
This must be equal to d.
So, all that is there on the
right
hand side must be an exact differential. Okay. If it is exact differential, then you have canonical transformation. Otherwise, you don't have canonical transformation. So, this can be thought of as a condition for the transformation or condition for checking whether given is a canonical transformation or not. Fine. Now, if I express f as function of q and capital Q, remember this. It may not be always possible to write capital F as a function of two n variables of your own choice. For example, if I have transformations which are like qi is equal to qi pi is equal to pi. The identity transformation. In this case, you can immediately see that if I have original function which is function of q, p and t, I will not be able to write this as function of q, capital Q and T. So, for this transformation, we won't be able to do that. Wherever we can do that. And then there will be other ways of handling the problem there. So, let me for the time being assume that you can express this f as function of n old generalized coordinates canonical coordinates and new canonical coordinates. Okay. So, that means if this is the case, then you can immediately write down pi. And what must be pi? Pi is nothing but partial derivative of f with respect to qi. And what is capital Pi? Capital Pi can be written as minus del qi. And also k minus h is equal to partial derivative with respect to t. Okay. Now you turn this around. What we started with was this. I have a canonical transformation. I derived a condition. That some expression here is an exact differential of some f. Now let's invert the problem. Suppose I give you this. Okay, I give you this. And I give you this function. Calculate now pi by taking derivative of this. What will this do? It will give you pi in terms of, remember these are small pi's, in terms of qi or q and capital Q, because f is a function of q and capital Q. It will also give you capital P. So, I will write this as capital Pi as some functions of q and q. And it also tells you how to transform k, which is function of q, p and t as H
as H
plus
plus
del f
del f by del t.
by delta. Okay.
Okay.
What has happened?
What has happened?
So if I start with
So
a function,
if I start with a function
of small
function
q and
of
capital Q,
small q and capital Q,
I automatically get
I automatically get
a canonical
a
transformation.
canonical transformation.
Okay. So the problem
Okay. So the
has been
problem
reversed.
has been
Initially we
reversed.
started with canonical
Initially we started
transformation.
with canonical
We wanted to
transformation.
ask
We wanted to ask
whether it's
whether
canonical or not,
it's
for
canonical
which
or not,
we needed
for
to
which
find
we
one
needed
function
to find
f
one function f
whose exact differential
whose exact
is given
differential
by this right hand
is
side.
given by this right hand side.
Other way around, I give
Other
you
way around,
f.
I give you f.
From f, you
From
can
f,
actually
you can
generate
generate
a canonical
a
transformation.
canonical
you
transformation.
get these equations,
You get these equations,
and now I can rewrite these equations so that q
so that q
is expressed
is expressed
in terms of small q p and
small
t,
q p and
pi
and
is already
pi
there.
is
So
already there.
It will be a function
So
of
it will be a
q
function of q
p and
p and
okay. Of course, there was a t here which I forgot to write.
Okay.
So you see what happens here.
So you see what happens here.
Now here
and
I
here
forgot to write
I
this
forgot to
variable
write
t.
this variable
Okay.
t. Okay.
So that's why
That's
these
why
functions
these
are
functions
called as
are
generating
called as
functions.
Generating functions.
Generating functions
Generating functions
of canonical
canonical
transformation. So any given function of q and capital Q will generate a canonical transformation. But is this the only possibility?
Only possibility.
How about starting with a function
which is
capital F, which is
capital
function
F,
of
which is
instead
function
of
instead
small
of
q
small q
instead of
instead
q
of
and capital
q
Q,
and
I
capital
start
Q,
with
I
q
start with q
and capital P.
and capital P.
Will I still get canonical
Will I
transformation?
still get canonical
Oh yes, I will get equations like this.
I will get equations like this.
I will come to that in a moment. But you see, to do that, to get
pi
and pi, capital
and pi, capital
in
Pi,
terms of
the set,
it is crucial
that you
express this capital F function or generating function as a function of n old variables and new variables.
and
If
new
you don't
variables.
do that,
If you
then
don't
you
do
don't
that,
get a transformation,
then you don't get a transformation
between new set and the
new
old
set and the
Okay?
old set.
Fine.
Okay, fine.
Now let me take one example
let me take one example
to decide whether
decide
or to apply
whether
this
or
condition
to
of
apply this
canonical
condition of
transformation.
Canonical transformation.
Okay. So in the example, let me say that you have old set. So I will of course stay with a very simple example with only 1 degree of freedom. So let us start with a phase space which has two variables q and p, and we are going to map them to capital Q and capital P. Okay. Let me write down the transformations. So the transformations are capital Q is q cos alpha minus p sin alpha, and capital P is q sin alpha plus p cos alpha. Okay, so I have got this transformation. It's like a rotation in QP plane. Is this canonical or not is what we want to see. Okay. Now, start by first transforming this such that, so I want to write small p and capital Phi as a function of small q and capital Q. Okay. So, that I can do very easily. From this equation, I can immediately write down p must be equal to q minus q cos alpha divided by sin alpha. Okay. And use this p now here. So, then capital P will be q sin alpha plus minus q plus q cos alpha into cos alpha by sin alpha. And you can immediately see that as a coefficient of q, you will have sin square plus cos square alpha, and that of course will, so this will be q minus capital Q cos alpha. Okay, right. So we have written this. Now we want to check whether P dq minus capital P dq and plus k minus h must be equal to some exact differential. And we know from calculus, how do I check whether given differential form is exact or not? Well, that means the conditions which we have are del P, capital P, by del Q must be equal to del of small p, capital Q. That's one condition. The other condition would be del P by del T, remember this is small p, must be equal to del of k minus h by del Q. And the third condition would be del of minus p with respect to t also must be equal to partial derivative of k minus h with respect to capital Q. And we already know that this is equal to 0. We already have the transformations here. So small p and capital P, they do not depend on time. So these two are already 0. That means k minus h does not depend on q or it does not depend on capital Q. It must be only function of sum. So k minus h must be equal to some function of t alone. It doesn't depend on p and q. Okay? And that of course g of t you can choose because it's an exact differential. So if you can write this as g prime t or g dot t dt, and you can take it to the other side. So here I can write this as k minus h is equal to some, you can choose that as 0. But focus on this condition. This will tell you whether it's canonical or not. So derivative of p with respect to q. So derivative of p with respect to q is with a minus sign is 1 over sin alpha. And derivative of small p with respect to capital Q is equal to minus 1 over sin alpha. And yes, this means that the entire expression here, this expression is an exact differential. So this transformation here is a canonical transformation. And for any given h Hamiltonian, you can always construct a new Hamiltonian k by simply equating the two. Okay, remember when I equate them, I must write capital K eventually in terms of capital Q and capital P. But that's fine. I mean that you can do using the transformation equations here. Fine. Now coming back to the last point, remember the condition for canonical transformations is given by, you have pi dqi minus pi dqi minus plus k minus h dt. This must be equal to some exact differential. And then we had said that this should be function of q and t. But you see what we can do as this. Now I can write this as sum over I pi dqi, and I will replace this by minus sum over I qi dpi plus k minus h dt is equal to df. This is, remember, function of q, q and t, but because I have, so I am using this d of sum over I p I q I is simply equal to sum over I p I d of q I and plus sum over I q I d p I. So, what will happen is you get that extra term here, which I can transfer to the other side, and minus you have d of sum over p I q I, okay. And I will write this as d of f minus sum over I p I q I. And then of course, use the transformation equations to rewrite this. You can rewrite this as function of now small q and capital P and possibility. Okay. So, you see, now I can generate the canonical transformations in many different ways. If I want to generate a canonical transformation where I get new or old momenta and new canonical variables, canonical coordinates in terms of the old momenta and the new coordinates, and that you can do easily by doing something like this. And you can of course do that in 4 different ways. Remember, you are supposed to choose one set from the old coordinates or old variables, one set from new variables. And remember, you do not even have to stick to, you see, all q i's from the old set and all capital Q i's from the new set. You could actually mix them. So, there are actually many different ways in which you can write the generating function and then generate the entire canonical transformation. I will list out these main 4 ones, which are in the form of capital small q, capital Q and T, which we discussed earlier. This is the one which we just now wrote down, or this one or this one. And in each one of these cases, you of course get, in the first case we have seen small p I and capital P I written as partial derivative of f with respect to q I and partial derivative of f with respect to capital Q I. In the second case, remember, now you will get small p I, but capital Q i's from the generating function, and then of course you rearrange them so that you get transformation from old to new transformation. And in each one of these cases, what is given here is a trivial generating function. In the trivial generating function, look at the first one. If I take f1 as sum over q I and capital Q I, product of q I and capital Q I, then the transformation equations are these. What are these transformation equations? This basically changes the or interchanges momenta and coordinates. So, the new momenta were actually old coordinates and new coordinates are actually old momenta, except for a minus sign, and it is like a a restatement of the fact that we have been telling right in the beginning, that in the Hamiltonian mechanics there is no such thing as momenta and coordinates. They are all treated on same footing. You can keep on switching between momenta and positions. Of course, we will worry about, we are thinking of all these quantities as dimensionless quantities, we will worry about the dimensions in a different way. But the statement here is that both momenta and coordinates, they are same. Look at the second case. In this case, of course, we generate an identity transformation. The last one is again the same as the first one. this one here, what is this operation? Where new coordinates are minus of the old coordinates and new momenta are minus of the old momenta. Now, this is nothing but a parity transformation. Okay. So, in a most trivial cases, these 4 special cases will generate the well known transformations there. Okay. In the next section, what I will do is I will look at a non trivial example where we see that this canonical transformations can be actually put to use and get the solutions just the way we had described it in our motivation slide in the beginning.